can be solved by using equilibrium equation. It means that we need to solve for the two redundant value first, using the flexibility method. Okay. And we actually solve for the redundant using compatibility equation. And compatibility equation is derived from the principle of superposition. Applying principle of superposition, okay, the general equation, actual structure equal to primary structure plus redundant structure. Redundant structures. And for this case, for second redundant, we may have more than one redundant because of redundant in the system. There are 5 unknown reaction and only 3 can be solved using equilibrium equation. So we have two degree of indeterminacy. So these two have to remove from the system, and we need to solve for these two value first. Okay, let's say we analyze this. Beam like this. Alright, so let's say this is 10 meter, 20 kilonewton per meter. This is A, B, and C. Okay. By referring to this beam, if we check for the reaction, reactions here, we have MA, we have AY, AX, BY, and CY. Okay, this is 5 unknown reaction in this beam. Okay, please remember that whenever we remove the redundant, we have to make sure that the redundant the structure become determinate and stable. So we will have three possible primary beam for this case. Number 1, we we have cantilever beam plus by plus cy. Possibility number 1. Number 2, we have this one. It is cantilever beam. Number 2, we have simply supported beam like this. We have simply supported beam. Okay, at fixed support we remove moment so that the fix become to pin. So it is now pin here like this. Okay, we miss this. To get this primary beam, we remove MA and BY. This is the second possibility. Okay, next we have the third possibility. Again, simply supported beam. The third one is like this. Plus MA plus CY. Okay, all this is the primary beam. As well as this. Okay, so let's say I want to choose this one. Okay, to derive the compatibility equation, I choose possibility number 1. So BY and CY is removed. Okay. Taking possibility number 1. BY and CY as redundant forces. General equation. It is actual beam equal to primary beam plus redundant beam. Redundant number 1 is redundant BY applied plus redundant CY applied. Okay. Okay, we will derive the compatibility equation based on this general equation. Then the general equation is based on the principle of superposition. It is actual beam equal to primary beam plus redundant By applied plus redundant Cy applied. Okay, after removing By and Cy applied, the beam become cantilever beam subjected to UDL. Yes. This is cantilever beam subjected to, this is ABC plus wait, I want to start from actual beam. Actual beam, we have roller here and roller here. Okay, this is A, B and C, and this is equal to primary beam. Primary beam A, B, B, C plus redundant By applied means a cantilever beam subjected to a unit value of By. A unit value of By plus a cantilever beam subjected to a unit value of Cy. This is A, B, C, A, B, C. Okay, what we need to do after we draw these four beams, okay, I want to draw the deflection for each diagram. Due to UDL for actual beam, we will have like this. Okay, deflection for primary beam is like this. Deflection due to for cantilever beam subjected to a unit value of By is like this, and the last diagram is like this. Okay, so what we need to do now is, since this one is force, this one is also force, means that we need to look at to the delta at B and delta at C. Delta at B and delta at C for each diagram. Okay, at B, since this is roller here, there is no value for delta, is equal to 0. Same goes to C, delta C is equal to 0. For primary beam at B, due to UDL, delta here. Okay, for redundant By applied and redundant Cy applied is also same. Okay, this one is referring to all the displacement that occur in the system. Okay, for this is actual beam. This is actual beam, primary beam, and this is redundant BY applied, and this is redundant CY applied. Okay. In the primary beam, there are two displacement at two redundant position. Okay, here we have delta at position B for redundant beam B0. Delta B0. Delta B0 means deflection at position B for primary beam, and at point C it has delta at position C for for primary beam. Okay, delta is deflection. We use delta because the redundant is forces, redundant for BY and CY is forces, so we need to determine the delta. We have to look at to the two position, which is at B and at C, the redundant position. So at B, there is delta at position B for primary beam, and at C, delta at position C for primary beam, it is delta C0. For redundant BY applied, at position B, due to a unit value of BY, the delta is F, is called as F. F is for the flexibility coefficient. Alright, this is F at position B for redundant BY applied, FBB, and at position C, it is F at position C for redundant BY, FCB. For redundant BY applied, and for redundant CY applied, it is also F due to a unit value, delta become F due to a unit value of BY or a unit value of CY, delta become F. It is F at position B for redundant CY applied, and at position C, it is F at position C for redundant CY. Okay. Okay, by looking at this, we will write the equation, two simultaneous equation. If in one redundant system, we derive one equation based on number of redundant. So for two redundant system, based on the two redundant in the system, we will write two simultaneous equation. The equation is right based on the redundant position. So we have B and C as the position of redundant. So we will write the equation 1 and equation 2. Remember that in actual beam, in actual condition, at B and C, there is a roller support. So delta at B and delta at C is equivalent to 0. In the primary beam is a determinate beam after removing redundance from the system. Okay, it become cantilever beam subjected to UDL. at position B, the delta is delta B naught. It is represent the deflection at position B for primary beam, and at position C, it is delta C at position C for primary beam. For redundant By applied, due to a unit value of By, the delta is now F, and it is FBB because F at position B for redundant By applied, and at position C, it is F at position C, FCB, F at position C for redundant By applied. And the last one for redundant Cy applied, at position B, due to a unit value of Cy, at position B means FB because the first notation is used for the position and the second notation is used for type of beam. So it is become FBC. And at position C, it is FCC because it is F at position C for redundant Cy applied. Remember that F is representing displacement since the redundant is forces. Okay. Based on this, we can write the two simultaneous equation. Equation number 1 will be based on point B, and equation number 2 will be based on point redundant number 2. Okay, like this. We will have equation 1. Okay, we start with primary beam because it will equal to 0 because 0 is in actual condition. So start with primary, it is delta B naught plus FBB times with By plus FBC times with Cy, and this is equal to 0. Okay, remember that this equation will be based on position redundant number 1, which is at position B, and here the first notation is for the redundant position. The first notation is for the redundant position. Okay, for equation number 2, it is delta at position C for primary beam plus, okay, this one plus FCB kali By plus FCC kali Cy equal to 0. FCB times By plus FCC kali Cy, and this is equal to 0. Remember that for equation number 2 will be based on position redundant number 2, which is at position C. So then the first notation is referred to the position. So let's look at this. This is position C, position C, position C. Okay, these two simultaneous equation, I want to rewrite it back into the standard form of compatibility equation in flexibility matrix, which is in matrix form. Okay, I want to rewrite it back in this form. Start from primary. So this is the standard form of compatibility equation. For two redundant system, it is like this: delta B naught, delta C naught plus FBB, FBC, FCB, FCC times with BY as the first redundant and CY as the second redundant, and this is equal to 0 in actual beam. Okay, this is the compatibility equation when BY and CY is redundant. Delta B naught and delta C naught, delta B naught and delta C naught here are representing the two displacement in primary beam, FBC, FBB, FBC, FCB, and FCC. In this form, this is called as flexibility. This is called as flexibility matrix. Okay, BY and CY represent the redundant, BY as the first redundant and CY as the second redundant, and this 0 is represent delta at B and delta at C respectively. However, by having this equation, this is only true for BY and CY as redundant. What if other redundant is chosen? Okay, let's rewrite this in general form. In general form means I want to change redundant 1 as number 1, redundant 2 as number 2. Means B as redundant 1, I will change to 1. C as redundant number 2, I will change to 2. So that we will get one general form of compatibility equation that is suit to all types of problem. Okay, so since BY is redundant number 1 and CY is redundant number 2, so I want to rewrite the compatibility equation. This equation I want to rewrite it back in the form of 1 and 2 to represent redundant. It is like this: all B symbol I will change it to 1, and all C symbol I will change it to 2. Okay, it will become like this: delta 1 naught, delta 2 naught plus FBB will become F11, FBC will become F12, FCB will become F21, and FCC will become F22. And this is for redundant 1, for redundant 2, and this is equal to 0. So this is actually the general form of compatibility equation that will suit to all problems. For example, if redundant 1 is by, redundant 2 is cy, I can straight away write the compatibility equation like this. Delta 1 not, delta 2 not, plus, this is standard form of matrix, 1 1 1 2, 2 1 2 2, 1 2, 2 1, 2 2, times with, I want to put the name of redundant right here. I want to put by here, cy here. Also can like this. Alright. If referring to the same example just now, I want to choose other reaction as redundant. R1, redundant 1 is MA. And redundant 2 is by. So, for the compatibility equation, I will have like this. Delta 1 not. Is it delta? No. This is not delta because this is moment. So, it should become theta. So, it is theta. Theta 1 not. And this one is delta 2 not. Plus this one is standard F11, F12, F21, F22 times with the first one is MA. I put the name of redundant here. I prefer to put the name of redundant here. Is for us not to be confused. So now if we look at this as moment, this should be theta. Like that. Okay, so this one is by, and it is equal to 0. Like this. Okay. In this compatibility equation, there are six displacement. All this is displacement. This is displacement. Displacement, 1, 2. This 2 is in the primary beam, primary structure. Okay, this is another displacement, 4 displacement in the two redundant system. Means that we have to solve for 6 value of displacement as mentioned previously in the previous example. Okay, what is theta 1 not if it is for beam and frame. Okay, we integrate to determine the deflection. We adopt the concept of principle of virtual work here. So the equation is, the formula is like this, 1 over EI from 0 to L. You look at to the notation that we use, 1 naught referring to M1 times M naught come from the two system dx. Theta 2 naught, delta 2 naught is 1 over EI from 0 to L. 2 and naught means M2 and M naught dx. Okay, we have F11, 1 over EI from 0 to L. 1 and 1 means M1 times M1, M1 squared dx. Okay, we have F12 is equal to 1 over EI from 0 to L. 1 and 2 means M1 times M2 dx. And it is equal to F21. And we also have last one is F22 is equal to 1 over EI from 0 to L, M2 means M2 squared dx. Okay, this is the formula. We get this M0, M1, M2. So we have M0, we have M0, we have M1, we have M2. M0, M1 and M2 is, okay, these are moment equations from primary structure, redundant 1 and redundant 2. Okay. Okay, let's do one example. Let's say I have beam. Sorry, I want to choose frame. Okay, frame. I have frame like this. Fix here, pin here. Okay. This is 10 meter. 10 meter. This is 25 kilonewton per meter. Okay, this is A, B, and C. Okay, we know that for beam and frame to remain stable and determinate, by looking at the support, it has 5 unknown reactions, so we need to remove 2. If I want to remove 1 from A and 1 from C, at A I remove MA, at C I remove CX. So it will become like this. I want to remove MA, so for redundant 1 is MA. And I want to remove CX, so at C, CX is the redundant. Okay, now I have already chosen the redundance. So by having this as redundant, I should be able to write the general form of compatibility equation. And it is delta, sorry, not delta because of moment. It is theta 1 naught. I use the standard form. Delta 2 naught plus, this is standard flexibility matrix. It is F11, F12, F21, F22 times with the first one is MA, the second one is CX, and this is equal to 0. This is equal to 0. So this is the standard form of compatibility equation. From this, we know that we will determine MA and CX first, and after we have determining MA and CX, the remaining 3 unknown reaction, the remaining reaction in this frame can be solved using equilibrium equation, or we can also use principle of superposition. Okay. So by having this, we know that we need to have, in order to solve for the redundant, since we know that solving compatibility equation produce the, in order to solve for the redundant, since we know that solving compatibility produces the redundant we need to have 3 determinate frames. We should have primary frame, we should have redundant system, which is called as redundant MA applied, and we will have redundant CX applied. Okay. For primary frame, okay, we have frame. Now A is become pin because we have removed moment, so this one is become roller. So we have 3 same frame. Copy, paste. Okay, what is different in these 3 frames is only for the force. Okay, primary frame, for primary frame, the primary frame is subjected to UDL, external loading. For redundant MA applied, it is a frame, a determinate frame subjected to a unit moment at A and here a unit value of CX. So this is MA, so this is CX. So what we need to do here is we have to write the moment equation, because in the formula we need to have moment equation. We know that from this equation, 1 knot is referring to M1 kali M knot, 2 knot is equivalent to M2 kali M times M knot, means that we have to have moment equation, and moment equation we will get from these 3 primary three determinate frames. Okay, here we need to determine the reaction, and after that write the moment equation. Okay, the moment equation in the primary frame is M naught. The moment equation in redundant number 1, redundant MA applied is redundant number 1 is M1. And the moment equation for redundant CY applied, since CY is the second redundant, this is M2. Okay, so if this is A, B and C, A, B and C, A, B and C, okay, we have to write, we have to solve for the calculate reaction in these 3 systems. After we calculate reaction, we have to write the moment equation. The moment equation in the primary frame is M naught. The moment equation in the redundant number 1, redundant MA applied, is M1. And the moment equation in redundant number 2, redundant CY applied, is M2. So we tabulate all the moment equation like this. Member, origin, limit, we have M naught, we have M1, and we have M2. So The member is AB. Member here is referring to the cutting section and BC. Origin at A for AB and at C. Choose the easiest section. Limit is from 0 to 10. 0 to 10. So we just need to fill in this table with moment equation, and after that we just need to substitute into the formula. There are 6 displacement that we need to determine. After we determine the 6 displacement, we have to substitute into the compatibility equation, then we get the redundant value. Okay, after that we just have to determine in terms of EI, because EI will be cancelled. In terms of EI, we have F11. Also in terms of EI, F12, F21, in terms of EI as well, and F22. So we just need to substitute all these 6 value into the compatibility equation. Substitute. Substitute 6 displacement values into the compatibility equation, and remain in terms of EI. Remain in terms of EI. Then solve. Solve the compatibility equation for the redundance. Finally, the remaining reactions in the pictures can be solved by using the Prince equilibrium equation from position. Okay, that's all for today. Thank you. Okay, that's all for today. Assalamualaikum warahmatullahi wabarakatuh.